Good afternoon, everybody, and welcome to today's expert webinar on galvanized rebar and bolts, hosted by the Africa desk of the International Zinc Association. I'm Shannon Derejo from Creamer Media's Contract Publishing, and I'll be your host this afternoon. Today, we will address the critical role that hot dip galvanizing plays in the protection of reinforcing steel from corrosion in concrete and the vital importance of using hot dip galvanized steel bolts on steel structures exposed to corrosive atmospheres. Registered professional engineers can earn extra CPD points by participating in the webinar. We have three specialists presenting this afternoon, and we will introduce them as we proceed. You will see that we have enabled the Q&A function, so please post your questions into the Q&A box. You'll find this on the panel at the bottom of your screen. The panelists will answer as many of your questions as possible at the end. We are recording this webinar and we'll be sending the recording to you when it's available, so don't worry if you miss anything. You can also interact with the panelists and other attendees in the chat box, which you'll also find at the bottom of your screen. As this is an interactive workshop, we've also enabled the raise your hand function, which will allow you to chat live with the panelists. So let's get started. Our first speaker this afternoon is Simon Norton. Simon is a chemist and a corrosion and failure investigation expert who also manages the International Zinc Association in Africa. Simon will provide a refresher in zinc chemistry as it applies to galvanizing. Simon, I'll let you know when there are 3 minutes left of your allocated time, so it's over to you.
Thank you very much, Shannon. Good afternoon, ladies and gentlemen. Welcome to our webinar. I hope we don't provide you with too much information to blow your mind, but we hope that you thoroughly enjoy yourself. Please ask as many questions as possible. It's your webinar, and we're here to give you all the information and advice and guidance that we can, so that you can use zinc and galvanized materials. So let's start off with looking at some chemistry. Later on, Terry Smith's going to be talking about bolts and fasteners and galvanizing as it applies to it. And Martin Gagne is going to be talking about reinforcing steel and galvanized reinforcing steel. But before we do that, we need to understand the chemistry of zinc as it applies to those applications. So here goes. Let's do a bit of chemistry. Shannon, am I screen sharing?
It's not sharing yet, Simon.
Okay.
Just let me know if you'd like me to share from my side. I can also do that.
It should be sharing now.
It's coming. Yes.
There we are. Right. A refresher course in the chemistry of zinc and how zinc provides corrosion protection to your steel. Now, in a very short space of time, I'm going to compact all the materials that relate, the information that relates to zinc and its applications in galvanizing. If you look at the periodic table, and I know many of you as engineers find chemistry something rather difficult. However, I'm sure you're familiar with the periodic table, and you'll see that zinc is listed as a transition metal. And if you look at some of the neighboring elements, it's right next to copper, silver, cadmium, gold, mercury, nickel, palladium, platinum. They all sit in the periodic table. As you can see where my cursor is moving, you can see all the different elements, and there are a whole lot. The whole pink group are the transition metals, but there sits zinc. And if you look a little bit closer at zinc, zinc has got an atomic number of 30. That means it's got 30, zinc atoms got 30 electrons and 30 protons. So it's perfectly electrically balanced. It's zero, it's neutral. Its atomic weight is 65.38. So a mole of zinc will weigh 65.38 grams. Its electronic configuration is shown in short form with the format of the electronic shells of argon, and then the 3D shell and the 4s shell. Now, this is very important because the 4s shell is actually the two electrons that are most easily removed from zinc, and that is the secret to zinc's operation as a material in galvanizing, because once those two electrons leave, zinc is oxidized. But we'll come back to that in a minute. Its crystal structure, it's hexagonal when it's in a solid state. Its physical state at 20 degrees C is solid. It's got dual acid-base properties, which I'll talk about in a minute, which will become more apparent to you as we go on. Now, the key to the use of zinc in galvanizing is what we call the Galvanic Series. Zinc provides not only a physical barrier on steels, which Terry Smith will talk about when he speaks about bolts, and Martin when he talks about reinforcing in concrete, but it also acts electronically or electrically or electrochemically, if you want to call it that, in the galvanic effect that it has. If you look at the simplified Galvanic Series of all the different materials or metals in seawater, you'll see at the top that the least noble sits magnesium, aluminium, and zinc. So if you look on the right-hand side of the diagram, you'll see that, and let me get my cursor to show in where the red marker is, you'll see that that's the direction of attack. So the zinc will be attacked, and the steel, here it is, steel sits over here in the Galvanic Series. Now this is a very simplified form in order to illustrate the principle of galvanic protection by zinc. You've got steel sitting over here, and you've got zinc sitting over there. Zinc is least noble, so zinc corrodes preferentially, and steel remains protected. If you link up various materials together, you've got to be very careful. For instance, if you take stainless steel that's passive, it sits over here. But if you take stainless steel that's active, it sits over there. So you have to be very careful in your design work as to how you choose and select combinations of materials. But that's for another occasion when we're talking about galvanic action in corrosion. In this case, we're talking about zinc and its links to steel and how it protects it. If you look at this more detailed Galvanic Series in seawater, you'll see across the top of the diagram the voltage measured against what's called a saturated calomel electrode. It's a simple thing. It's a reference electrode. So we compare the material in seawater against a reference. And there on the right top side, you can see zinc. There you see clean, shiny, mild steel sitting there, just below 0.6 of a volt. In electrochemistry, we tend to work more in millivolts. So we're sitting there somewhere between 550 and 600 millivolts, zinc sitting up here. And then you could see all the other materials down the Galvanic Series. To the ones down here where I'm showing the cursor, those are the materials that are most noble and we term cathodic. So zinc is anodic and it provides cathodic protection to steel. And that is its function in its galvanic function, its electrochemical function when it works with zinc galvanized over steel. Now, zinc has got another property. When zinc is exposed to the atmosphere, it automatically forms zinc oxide, and with there being moisture in the atmosphere, zinc hydroxide. And we term a material such as zinc oxide as amphoteric oxides because it can react as an acid and as a base. So let's look at it as an acid. Here we have zinc oxide as an acid reacting with sodium hydroxide, NaOH, and the AQ means in solution, aqueous. The zinc oxide, S means solid. Here you have an alkali, there you have an acid. Now you know from your early school chemistry that an acid and a base gives you a salt plus water. So here you have an acid, zinc oxide, a base, sodium hydroxide. It forms sodium zincate, which would be a salt, you call it a salt, and water. So in this role, zinc oxide, which is already formed, immediately zinc is exposed to the atmosphere from the oxygen in the atmosphere, is acting as an acid. But equally, zinc oxide can also operate as a base. So in this particular case, zinc oxide is an alkali reacting with hydrochloric acid in aqueous solution, which is an acid, to form a salt, zinc chloride, and water. Now, this role, the amphoteric role of zinc, is critical to its functionality in reinforcing steel. Martin will speak about that later. But just remember, zinc is amphoteric. And for those of you busy with design in other materials such as aluminium, aluminium is also amphoteric. aluminium oxides function in exactly the same way that zinc oxides and zinc hydroxide function in acids and bases. Aluminium is amphoteric, the oxides, and so is zinc. Now, today we're going to be focusing on the protection of rebar in concrete, bolts and fasteners by means of hot dip galvanizing. And the key chemical element is zinc. So let's look at reinforcing steel from the chemical perspective. Here you see a complete structure laid out with reinforcing steel. I'm almost certain this is galvanized, although I stand corrected, but it probably is, because normally rebar is already rusted with iron oxide on it before it's laid down. So this is probably galvanized. But I'm not going to be discussing that. Martin's going to discuss that. I'm going to be talking to you about the chemistry of zinc. Now, inside concrete, when concrete is first laid down, there's your piece of rebar. The pH of concrete is greater than 12.5, and the whole environment or matrix is passive. Now, if you're sitting at Cape Town or Durban, Port Elizabeth, or on the coast, or you're in an area where there's substantial wind or effect of the atmosphere in movement, and it's not a still environment, and it's an open atmospheric environment, gradually you will get a change that occurs in the concrete. And what happens is the carbon dioxide in the atmosphere starts to penetrate the porosity of the concrete to form a carbonation front, which you see here. Equally, chloride ions, if you're near the sea or another environment where there's chlorides, will start to penetrate through the concrete. And if you have a look over here, you'll see there's the concentration of free chloride. And as you go further into the concrete, you find that you've got a safe concentration. There's your rebar, and it's fine. However, going back to the amphoteric zinc, if you had galvanized your rebar, you would then find that as the carbonation moves through the concrete, the pH of the concrete will change, and the pH will come closer to a low pH. So in this particular case, zinc being amphoteric, if you galvanize your rebar, will react with a pH of 12 material. But equally, if there's an acid environment, because the pH lowers because of carbonation, you'll get a reaction. That's the amphoteric nature of zinc. But that's for Martin, and I won't go on further than this, but merely to say to you that the amphoteric nature of zinc's chemistry, zinc oxide's chemistry, it comes to play in the use of galvanized rebar in concrete. Now, if you look at a piece of rebar in water, and this has got a generalized application to all steel. If you have a look over a rusted surface, before it rusts, there are scores and thousands of anodes and cathodes all over the surface. At the anode in water, the iron is oxidized to iron 2. It releases electrons. In this case, we have a balanced oxidation reaction. We have 4 electrons. Those 4 electrons then move over to the cathode on the steel surface, and water and oxygen are reduced. If you have an ability to stop the cathodic reaction over here, then you halt the whole corrosion process. If you can halt this process over here, you also halt the corrosion process. And hence you would use things like galvanizing of rebar, or corrosion inhibitors, or corrosion passivators. But we're not going to be speaking about that. We're just talking about the generalized effect of water on steel. In this particular case, a mock-up of a piece of rebar. Iron goes to iron 2, electrons are released, the iron goes into solution. Over here you get reduction, so this is oxidation at the anode, reduction at the cathode. Forms hydroxides, reacts with iron to form iron hydroxides, and of course iron oxides, and you have rust. Now, the other potent player in the chemistry that happens in concrete, because we're talking a little bit about that and it relates to zinc, is chlorides. Now, if you have a piece of uncoated rebar, and here on the green line is your increased profile of concentration of chlorides, at this particular point down here, the rebar starts to corrode, because of course you didn't design with galvanized rebar. Up goes the corrosion process, the stresses get greater and greater, eventually the concrete cracks and then it spalls. However, if you galvanize, because chlorides attack zinc, zinc goes into solution, it lets go of 2 electrons, and you get the formation of zinc chloride. So you get a formation reaction, a reaction happening between zinc and chlorides, and chlorides are very bad for galvanizing. However, if you galvanize, you will essentially withstand the effect of chlorides, and you can stand a higher concentration. Only at this point does corrosion start to take place. Your galvanized rebar only starts to show internal stresses over here, and hence you've protected it. So the chemistry of that chemistry is vital to protecting rebar, and the chemistry of zinc is vital to protecting rebar. But that's an upset on rebar. Martin's going to deal with that. If we look at the chemical impact of the atmosphere on galvanized steel, i.e. zinc-coated steel, well, this could be your bolt or your fastener, which Terry Smith's going to be talking about. This is some of the latest work that's been done on the exposure of zinc in an atmosphere, in a marine environment. And if you look on the left, you'll see here are all the compounds that form when zinc is in a sheltered marine environment over time. So there's your galvanized steel structure or your galvanized bolt. Initially, zinc oxide and zinc hydroxide form instantly, even before exposure to a marine environment, because of the oxygen in the atmosphere. Then the next compound that forms, because you've got carbon dioxide in the atmosphere, is this material here, which is called hydrozincite. This material then subsequently forms because you've got chlorides in the sea spray. This is actually called Simon collite as a mineral name. And finally, this material over here. What has been developed recently is a technique of looking at the interface between the solid galvanized steel, the layer of galvanizing, the zinc, and the deposition layer. So in the atmosphere, you've got oxygen, water, sodium chloride, sulfur dioxide, and chlorides. And they all react to form different materials. So you've got hydroxides, which are basic. You've got an acidic ion, you've got chlorides, and you've got sulfates. And they form all these compounds in the deposits on hot dip galvanized material. This surface model is called the Gilder's model, and it's a very interesting way of looking at the surfaces of galvanized and zinc-coated materials. And if you're interested in looking it up, then I suggest you give me a call or an email, and I'll send you a paper by Wallinder and Leeggraaf, which is a superb review of the state of the art of galvanizing and how it reacts in the atmosphere and runoff from galvanized surfaces. It's an excellent, excellent paper. So if you're in, for instance, if you're near one of the coal-fired power stations in the eastern part of our country or in the area around Gauteng, it's likely that the atmosphere is going to have a lot of sulfur pollution from sulfur dioxide from the combustion of coal or materials combusted in all the plants in the Gauteng, Johannesburg, Reef area. In that case, if you expose galvanized steel, it will react to form this material in the atmosphere, and then it will move up along this route here and form these materials because of the sulfate environment. What is happening in the rest of the world is that because sulfur dioxide and sulfates are being removed from the atmosphere, that this mechanism here is no longer as prevalent as this mechanism at the bottom is near the sea or near an environment where there are chlorides. So the bottom mechanism is more applicable to South Africa. Chloride pollution, Durban, at the Bluff, along the coasts, Cape Town docks, False Bay, coast in Cape Town, and other areas, the West Coast, Namibia, Walvis Bay, Lüderitz, all the coastal areas of Namibia. They will, if you expose galvanized steel in that environment, you'll go this route. And if you look at the bottom here, you'll see that this form starts to form within days, this material within weeks, and this finally within months and years.
Simon, you've got 3 minutes left.
Thank you. A new model is recently developed for zinc exposed in the European atmospheric environment, which is quite interesting. This equation, which I won't deal with in too much detail, but merely to expose you to the thinking that's going on, has a factor that the 0.9 factor is for the background corrosion. This factor over here with SO2, the relative humidity and the temperature, or the function of temperature, is what's called the dry deposition, because it's found out that as temperature increases, a certain point is reached where sulfur dioxide corrosion then stops, because it's very temperature dependent. However, if you have chloride corrosion, it is not, it increases as temperature goes up. And it's not in the dry depositioning part of the equation. And the last part here is this relates to rainfall and the pH of the rain and the role of nitric acid, which is now being recognized as having an impact on zinc. But be careful, this equation only applies to work done in the European Union, in European countries. Other areas might differ and other models might apply. But I thought I would show you how there's such a complex interaction of physical factors in corrosion of zinc. If you have a look at this diagram, you'll see on the left-hand side the corrosion products of zinc when exposed to the atmosphere. On the left-hand side, you will see in an unprotected marine atmosphere. So if you look at the galvanized steel, you can see immediately there's zinc oxide and then all the products that form. If you had galfan, which is a mixture of zinc and 5% aluminium, you get a different structure. And if you had an aluminium structure, you'll see that on the left. If you look at the coating on the left-hand side, again, the chemistry of zinc comes into play. The zinc coating is the anode, the steel is the cathode. The zinc forms corrosion products. If you've got a scratch or damage in your zinc coating, it blocks it up. The zinc is the anode and then oxidizes and protects the underlying steel. But if you have paint and you have a nick in the paint or a scratch or damage, the atmosphere gets through to the steel, the corrosion products form, they lift the paint, go underneath the paint and destroy the protection of your steel. So the moral of the story is first galvanize, then coat. And Terry will talk about that as duplex coating. So in summary, we've got zinc reacting acting as a barrier and acting electrochemically to protect your galvanized steel or your galvanized bolt. The zinc is oxidized into the solution. The damage here is protected galvanically. So you've got a physical barrier, a galvanic barrier, and the corrosion products of zinc also fill up these sort of gaps. So you've got a multi-layered protection when you work with zinc. So there you have it, a quick chemistry lesson on zinc and how its chemistry allows galvanizing to protect steel. I hope that you enjoyed that. If you've got questions, feel free to ask. If you've got other questions, please send me an email or we'll chat about it just now. Thank you very much.
Thanks very much, Simon. It certainly looks like it's back to the books for some chemistry before any of these engineers do any designing. So good luck with that. Our next speaker is Martin Gagne. Martin began his career as a research engineer at Dofasco Inc., then served as manager for market and product development at Noranda Inc., Falconbridge, and most recently for Xstrata Zinc Canada. He is involved in IZA's global programs in general galvanizing, die casting, and zinc oxide. Martin will focus on galvanized rebar, as Simon mentioned, and its importance in civil engineering. Martin, I will also let you know when there are 3 minutes left of your allocated time, so it's over to you.
Well, thank you very much, and I'm very happy to be here to talk about hot dip galvanized rebar. And so people are asking, why should we hot dip galvanized rebar? So this is a bridge structure from North America. We can see quite extensive corrosion. Concrete is porous, and so as as Simon mentioned, carbon dioxide can go in. Iron is quite passive at very high pH, but when the carbonation front arrives, it lowers the pH, which makes the iron susceptible to corrosion. And then chlorides, they can depassivate the iron and also start corrosion of the steel rebar. Now, the corrosion products of iron can take up 7 times the volume of the iron itself. So this is what puts pressure on the concrete. Concrete is very good in compression, good compressive strength, but very poor tensile strength. So when we put a lot of corrosion product build up around the rebar. That puts tensile stress, which causes the cracking and the spalling. Now, the chloride can come from the coasts. In this case, in North America, it's from road salts, the carbonation front that can decrease the pH of the concrete, but also saline soils. A lot of concrete structures are put on foundations for buildings, and South Africa, 30% of the soils are classified as highly saline. So whether it's dust from those soils that then get mixed with rain and cause a corrosive solution, that can have an impact on the structure. On this bridge, if we look at that rail on top of the concrete, that was hot dip galvanized. It's seen the same salt loading and atmosphere as the concrete, but it's in excellent condition. We can also see some power transmission lines in the background, some signposts, there's guardrails. A lot of these street furniture structures are hot dip galvanized. So it only makes sense to put galvanized rebar in the concrete to have the same corrosion protection. And it's not just for highway structures. There was just a fatal collapse of an apartment building in the state of Florida in the United States. Corrosion has been blamed for the cause of that. Here we see some balcony structures with spalling concrete because of rusting reinforcing steel. This is a liability hazard. And of course, for coastal structures, any pier structures or anything near the coast, the chloride exposure is quite high, which leads to corrosion of the rebar, building up stress inside the concrete, which causes spalling, exposing more rebar and accelerating the whole process. So how does zinc protect steel from corrosion? So we already saw the background. The first is a barrier coating. Zinc stands in the way of any corrosive atmospheres. Secondly, by galvanic protection, zinc will sacrifice itself to protect the steel. I'm going to go more in depth on this chloride corrosion model, although we've seen it already. If we look at the yellow line here on the left-hand side for stress, the stress builds up until it gets to a level where the concrete cracks, and that's represented by the dashed red line. The yellow line at the bottom, the horizontal line, is the time scale. So if we see the black uncoated, and then the green line is the chloride profile at the rebar surface. Concrete is porous. The chloride ions will migrate to the rebar. When they get to the uncoated plane, black reinforcing steel, there is a certain threshold amount of chloride, and when we exceed that, excuse me, the black rebar will start to corrode. The corrosion products put stress on the concrete, and the concrete cracks. As was pointed out, the galvanized rebar has a much higher chloride threshold. This is anywhere from 2 to 4 times, and actually in some examples we see it's much higher before the galvanizing starts to corrode. And it will corrode because that's its role, to protect the steel. But we can see the slope of the line for the galvanized rebar is much less than the slope of the line for the uncoated black rebar. And this is because the corrosion products on the galvanized rebar do not exert the same stress on the concrete. So it takes us much longer to initiate the corrosion, and then it takes much longer for the zinc to be consumed or for any stress to build up on the bar. Eventually the zinc will be consumed and the black bar will start to corrode. But this is what gives us such phenomenally long life using galvanized rebar compared to uncoated black rebar. Another point to understand is that zinc will passivate in concrete in alkaline solutions higher than a pH of 12.5. The zinc is passivated by the formation of a calcium hydroxyzincate. There is calcium in the cement paste. This reacts with the zinc, and we get these crystals that form on the surface of the rebar. So this isolates the zinc, and stabilizes the surface, and extends the time for corrosion initiation on the zinc. And this reaction starts in contact with wet cement, and it stops once the concrete hardens, generally less than 24 hours. I talked about the corrosion products on zinc. Here we've done some analysis we can see the cement reinforcing bar interface on the left-hand side, and we measure the concentration of zinc as we move away from that interface. So we can see in the cement paste, there's quite high levels of zinc, almost to 1 millimeter away from the bar. So rather than build up at the interface, the zinc corrosion products dissolve into the pore solution in the concrete and migrate away from the bar, so the stress doesn't build up and we don't have the same potential for cracking and spalling as we do on the plain black steel. So we can see that zinc protects rebar in a number of ways. It's a barrier coating, provides cathodic protection. There's a very high chloride threshold. We see the formation of the passive calcium hydroxyzincate. While bare steel passivates at high pH, it is more the probability for corrosion increases at lower pH. This is opposite for zinc. It has a much higher corrosion resistance at a neutral pH. So as the carbonation front approaches galvanized reinforcing steel, the corrosion resistance is actually increasing. We saw the corrosion product migration. So this has a number of benefits. It does not generate the stress at the interface, but it also densifies the matrix. So if there are chloride ions that are progressing towards the rebar, the concrete matrix now is more dense. It's harder for those elements to reach the steel. And there is indication that it does improve the bond strength of the galvanized reinforcing steel with the concrete as well. Now, the production of galvanized rebar is the same as for the production of any galvanized product. We clean the steel, we pickle it, we flux it, we immerse in molten zinc and then cool it. If there are any galvanizers in attendance, the main issue really is racking, it's material handling to separate the bars so that they can be galvanized cleanly. But this is really quite routinely done, and there is no special considerations apart from racking for galvanizing reinforcing steel. This is a cross-section through the coating of a galvanized steel. So the zinc reacts metallurgically with the steel. We call it a metallurgical bond. It forms some layers of iron, zinc, intermetallics. These are quite hard. It gives quite good abrasion resistance to the coating. Now, we do know that reinforcing steel is made mostly from recycled steel, and silicon is a very inexpensive strengthening element for steel. Although silicon can destabilize this coating and increase the proportion of intermetallics compared to the free zinc layer at the top. And this can have some consequences for forming the rebar, but it will still provide the same corrosion protection. In North America, the formation of or the production of galvanized reinforcing steel is covered by a standard specification, ASTM A767. It has two classes, mostly dependent on the diameter of the rebar. For thick rebar, a class 1 coating is required a minimum of 150 microns thickness of zinc. And for thinner bars, a class 2, which is only 85 microns, a minimum of 85 microns of zinc. And we can galvanize a number of reinforcing products, welded wire mesh. We can see some bundles of straight bars there on the left. We can also have some stirrups and ties. Some reinforcing products can also be manufactured. Here we can see some large column cages. So here the reinforcing steel is manufactured into the shape, and then the whole column will be hot dip galvanized. These bolt cages, these can be embedded into the concrete, and they leave the bolts proud for attaching other structures to concrete. I talked about forming rebar. This is for avoiding any strainage and brittlement in the galvanizing kettle. So the bar designation number on the left-hand side, 3, 4, and 5, this is 10, 13, and 16 millimeter diameter bars. So we can see the bar number and the corresponding millimeter diameters in brackets. But we can see for all of the grades and most of the bar sizes, we have to have 6 times the diameter of the bar as a bend diameter to avoid any strain age and brittlement effects. And for the larger bar sizes, we go up to 8 times the diameter and even 10 times the diameter at the higher strength steels. Now, there are 6 million metric tons of rebar produced in Africa each year, mostly in Egypt. I do not have the distribution of use of rebar in Africa. However, that is a potential of 300,000 metric tons of zinc. So there is a good market potential for the production of galvanized reinforcing steel. Now, for designing and structures to work with galvanized rebar, it is really, there's no change from working with black rebar. The same overlap links, same handling procedures, some corrosion protection coatings such as fusion bonded epoxy. They are sensitive to ultraviolet light, so they cannot be stored outside. They have to be handled very delicately because if we scratch the paint, we expose the steel. We don't have any of these restrictions with galvanized rebar. The coating is very tenacious and robust. And we should not have any issues for repairing or touching up the rebar, except if we have to cut it in the field. We should put some zinc-rich paint or some solder on those ends to protect them. Now, the bond strength of zinc with the concrete is very good. This is a graph from the University of California. They look at the bond strength between black steel and galvanized steel. The black bars are for black steel and the green bars are for galvanized steel, depending on the month of curing. So this study was repeated 3 times with different types of concrete, but we can see that the galvanized steel has superior bond strength over all conditions and all curing times. A similar test, but on a different sample. Here we took concrete beams and we bend them in a 3-point bend test, and we measure the slip, how far the rebar moves within the concrete beam. So we can see at a given stress level, and here I put the blue bar at 65 kilonewtons. The galvanized rebar has the least amount of slip, followed by the black bar, and then the epoxy coated bar has the most amount of slip. So now I'd like to show a few case studies. Galvanized rebar, really anywhere where there is the potential for exposure to chlorides or high salinity soils. So we get precast structures starting at the top left. This is actually a channel for water management, bridge decks, other transportation structures, specifically coastal infrastructures, water treatment plants, balconies. And then we can see some foundations being laid. Some examples, one of the most famous here is the Sydney Opera House. This building was opened in 1973. The white clamshells were protected with galvanized welded wire mesh, and they have been corrosion-free now for 47 years. This is classed as a prestige architecture building, and they did not want to have any red rust staining or any discoloration of the shells. Ironically, the foundation was built with black reinforcing steel, and that has been repaired twice in the same time frame because they were not protected against corrosion with galvanized reinforcing steel. Another precast structure, the Bank of Hawaii. Again, this structure is over 40 years old, and there's been no staining or any corrosion of these arches. These are a facade of the building. It provides a sun shade, so it's one of an early design to try to use passive cooling to minimize the energy consumption of the building. But there's only 1 inch of cover on these arches. We can see the detail on the right-hand side, very elegant and no corrosion. This is a bridge excuse me, a bridge deck in the United States. It was built in 1973, and the median was upgraded after 30 years for safety reasons. And so they had to jackhammer and water demolish the median to replace it. And the bridge was built with galvanized reinforcing steel, and they found that the rebar was still in near perfect condition after 30 years. So they just cast the new concrete right over the old rebar. Again, if another corrosion resistant coating such as fusion bonded epoxy had been used, it would not have been able to withstand that demolition process, and more reinforcing steel would have had to be added for the project. And now this project is approaching 50 years old and still no rebar maintenance required. The International Zinc Association has been following a number of bridges. We take core samples, so we drill a hole, we pull out the core, we look at the chloride loading in the concrete next to the reinforcing steel, and then we measure the remaining zinc thickness on the reinforcing steel. So we can see here for a number of bridges that are approaching 50 years old, the chloride loadings are quite high. We can see in one case, the Curtis Road Bridge, this is almost 7 times the chloride loading for black steel, but the zinc coating is still in good condition. The latest bridge that was sampled was the Tioga Bridge, built in 1974. We did a core sample last year, very high chloride loading, and still quite a lot of zinc left on the reinforcing steel. Now, the rebar coating thicknesses vary. Sometimes it's less, sometimes it's more. We can never sample in the exact same location. So this just reflects the variability of the product as it was delivered. But in all cases, we have a significant amount of zinc left on the rebar, and these bridges should go their 100-year design life with no corrosion on the rebar. Canada, being a Canadian, I have to say something. We have a long history of using galvanized steel structures. The Lizotte Bridge is an all-steel bridge, but it's the first fully galvanized bridge in North America. It's in the province of Quebec. Also in the province of Quebec, these 2 bridges on Autoroute 30, Bridge 13540 and 13577, one built in 1965, one in 1966, using galvanized rebar. These are concrete structures, and they are corrosion and maintenance free since that time. The photos are from a more recent construction. This is the Stoneham Arch Bridge. It's only 5 years old now, but the top photo, we can see the rebar configuration that was used in the concrete arch. And then on the bottom, we see the workers finishing the installation of the galvanized rebar on the bridge deck. This is a bridge example from Bermuda, a marine environment, very corrosive. The top photo shows the original concrete bridge built with black rebar in 1957. Repair work started 3 years after, and the bridge was actually demolished in 1980 after only 23 years of service because it was significantly corroded and not structurally sound. The bottom photo shows the new replacement bridge, which was built in 1982. Galvanized reinforcing steel was used in the concrete piers and the bridge deck, but also hot dip galvanized steel beams were used to support the bridge deck. So now this bridge is almost 40 years old and it's still in excellent condition. There's no staining, there's no cracking, spalling, and there's no corrosion of the hot dip galvanized steel beams either. So using zinc coatings, whether in the concrete or out, is an excellent choice for corrosion protection. Here in Mexico, this is a elevated highway that is constructed on the Gulf Coast between Veracruz. And we can see the right-hand photo. This is one of the cage towers that was galvanized. The photo in the left, we can see some of the cement towers that have been cast around those cages. There are 2 cages in the background that are still to be encased in concrete. Again, this was constructed in 2014. It's not that old, but the choice was made because it's a coastal environment and it needs protection from the coastal chlorides. Another global example in Singapore. Here, a wastewater treatment plant discharge pipe. They are, it's 5 kilometers long that goes into the ocean. So these pipes are 3 meters by 8 meters long, 3 meter diameter by 8 meter long. So we can see the size of them. These were actually manufactured from pre-galvanized reinforcing steel and then spun cast concrete. So there were 10,000 metric tons of rebar, and this has a 100-year design life lying on the sea bottom, so direct exposure to seawater. Now an example from South Africa. This is the Cape Town seawall. So here, the photo on the right-hand side, the wall was built in stages, and the right-hand side shows a section that was built in 1990 using galvanized reinforcing steel. For whatever reason, when the construction continued in 1995, they used black rebar. So this is the junction between those two sections of construction. And we can see this photo was taken in 2005 after 10 years, but there's some red rust staining. We can see some cracking of the concrete coming through on the black rebar side, but not on the galvanized rebar side. So again, in a direct comparison, the exact same environment, the galvanized rebar, even though it's older, is outperforming the newer structure constructed with black rebar. So the Zinc Association maintains a number of resources. There is a book I will recommend, Galvanized Steel Reinforcement and Concrete. This is edited by Professor Stephen Yeomans from Australia, and a brochure on the right-hand side, Hot Dip Galvanized Reinforcing Steel, a concrete investment. You can find information about these resources on a website that is maintained by the International Zinc Association, galvanizedrebar.com. And here, a lot of the case studies that I've shown are here, standards that apply to construction with galvanized reinforcing steel and other publications. So with that, I will finish and pass the microphone back to Shannon.
Thanks very much, Martin. I'm just going to stop your sharing quickly. Oh, there we go. Well, thank you so much for that very interesting information. We'll now be moving on to our final guest speaker, who is Terry Smith. Before I go on to Terry, though, I'd just like to send a reminder to our audience to send us any questions you'd like the panelists to answer at the end of the presentations. So we move now to Terry Smith. Terry is South Africa's leading expert on hot dip galvanizing. He currently consults to civil and design engineers and on galvanizing of steel structures and has been advising South African industry for the past 25 years. Terry will take a detailed look at why you should use galvanized bolts. Terry, as with the others, I'll let you know when there are 3 minutes left of your allocated time. So it's over to you.
Thank you, Shannon. I've just got a screen that's stopped working for some reason.
It was sharing just a few minutes ago.
Try this
there we
one.
go. Yes, we can see it.
Okay. Good afternoon, ladies and gentlemen. Interesting to hear Martin talking. I'm in fact involved with some of those structures in South Africa, and I'm sure we can talk quite a lot about other structures that I've been involved with in South Africa, where they've changed from black steel to galvanized rebar. We're going to talk about 4 types of metallic coated, zinc coated fasteners, including centrifuging or spin galvanizing, its durability in terms of metallic zinc coatings, slowly corroding barrier, and cathodic or sacrificial protection, which you probably heard from the other 2 presenters as well. We're also going to talk about novel bolt uses and nut uses, hinges, fixing for security, fixing against vibration or movement, holding down bolts and threaded rod, and finally the embrittlement of components. Metallic zinc coatings for bolts and nuts. You have zinc electroplating, often called electrogalvanizing, and simply called galvanizing. We're talking about metallic mechanical plating, shieldizing, and hot dip galvanizing. In spite of correct specifying, are you not tired of something like this, that you go onto site and you see your project having premature corrosion, where bolts, nuts, and washers and clamps and threaded rod are corroding, whereas the structure itself was hot dip galvanized and still looking good. Zinc electroplating, briefly, the component is immersed into a coating solution. DC current passes between component and cathode, which is the cathode, and the electrode, which is the anode. The coating is governed by several things: the current, temperature, chemical composition of the product, and also the process time. Metals that can be used: copper, nickel, zinc, and chromium, and we're going to talk a bit about zinc. Yeah, you can see a typical zinc electroplating process, where you have the anode and a cathode, an electrolyte which contains a zinc cyanide or zinc chloride, and once the circuit is closed, the coating solution plates onto the cathode and the electroplated item happens. So you can see the inside of a zinc electroplating plant with the various cleaning bars in their different form. And yeah, you can see the typical electroplating station. These items here are the anode hanging on, and these are bus bars, and obviously there's a coating solution and the things are plated. Zinc electroplating characteristics: smooth, bright, shiny silver or yellow or olive in color. Each of these colors have a different in terms of corrosion protection, slightly more advantageous the darker colors. Coating thickness generally less than about 10 microns. It's a mechanical bond. Corrosion control of a metallic zinc coating is a function of coating thickness. So the thicker the coating, the longer it will last in any particular environment. Hydrogen embrittlement of high strength steels must be prevented by heat soaking at about 200 degrees C for a certain time to drive off the nascent hydrogen. And you can see a typical micrograph of electroplated coating. You can see the mechanical bond. There's no iron zinc alloys there at all, around 8 to 9 microns. You can see a typical zinc electroplated bolt, which is a silver in color, and here's one which is yellow. Here's a typical coating thickness of that nut. Mechanical plating components greater than 1,000 MPa. Ultimate tensile strength, and tensile stress components caused by machining, grinding, straightening, or cold forming must be stress relieved prior to the process. Components are loaded into a rubber-lined barrel containing copper in a chemical solution. The barrel is tumbled at room temperature. Glass beads of varying size act as the impact media, and sometimes this is also called peen plating. There you can see the glass beads inside there. Zinc metal dust, according to the specified coating thickness, is added. Sorry. And the standard is ASTM 695. You can see a typical barrel, which is, as I say, rubber lined. And yeah, you can see a relatively sophisticated mechanical plating plant. There's one of these plating plants in South Africa, and they're up in Johannesburg. They do a good job. The characteristics: coating is smooth, uniform silvery appearance with a matte to medium bright luster. Coating process is rather slow, and it's a mechanical bond. Components are limited to less than or just on 0.5 of a kilogram each. Coating density, 25% less than hot dip galvanizing. Heat treatment can improve the corrosion control. Coating characteristically tends to be thicker on the flat surfaces and thinner on the exposed edges, and therefore it's important to specify the right coating thickness on the specified significant surface. Coating thickness depends on process time from about 5 to 100 microns. And some reason my camera stopped.
We can still see it, Terry.
Should be another bullet point.
Oh dear.
Yeah. Your camera hasn't stopped. It's just moved to the next slide.
It's trying to. Nothing happening.
Maybe there we go.
Oh, there we are. Sorry. Okay, the nuts must be tapped oversized if coating thickness greater than 30 microns is required. And there's no hydrogen embrittlement associated with high-strength steel, which is hardness, Vickers hard or Rockwell hardness of 32 and above. Periodizing. Pre-treated components are loaded in a rotating drum. Slight difference to this though, the zinc powder and inert filler, which is like quartz sand or corrodium, acts as impact media. Sorry, ladies and gentlemen.
Technical difficulties. Sorry about that, Terry. There we are.
Drum slowly rotates, heated. This is not room temperature, but the drum is heated, or the contents are heated to about 350 degrees C. Uniform diffused iron zinc or zinc iron alloy layer is formed. It's a matte or textured gray color coating. Coating thickness greater than 35 microns tends to flake. And there's a standard, it's a BSEN ISO 17668 or BSEN ISO 14713, which is part of the galvanizing spec. Okay, we're talking about centrifuge or spin hot dip galvanizing. I was involved with this project many years ago. You can see the size of these bolts, they M72. And you have some other big ones. M68 bolts, and in the center, standing on its head, is a M36 bolt. Minimum size bolt that can be hot dip galvanized is an M8. This is the process, which is standard process. Items are jigged, degreased, rinsed in water, acid pickled, rinsed again in water, and goes into a flux, which is your final cleansing action of your steel. It comes down here into a drying deck. The items get loaded into a basket, and that basket goes into the zinc bath, following the various other things which you'll see in the following slides. Then once the reaction has taken place and the coatings have happened, they are loaded into a centrifuge, and from the centrifuge, which rapidly spins and quickly breaks, removes the excess coating. They then quenched and cooled into an inspection area. So this is what happens. Suitably clean bolts and nuts and washers are loaded into steel baskets and immersed in a molten zinc at a temperature of about 450 degrees C. Zinc melts at about 419 degrees C. It's going to take our time. What happens? Steel achieves a temperature of about 450. Metallurgical reaction happens between the molten zinc and the carbon steel. And from the steel interface, we have various iron zinc alloy layers. And you'll see in the following slide, the gamma layer, which is right adjacent to the steel, the delta layer, the zeta layer, and the eta layer outside soft layer. So you have up to 25% iron in the first gamma layer, and the iron part of this iron zinc alloy layer gives you tremendous amount of abrasion resistance. And yeah, you can see mechanical damage unlikely due to the hard iron zinc alloys when we misuse spanners, etc. on site. Now you can see the items being loaded into the molten zinc. And the items, what they call routing. This is a hand process whilst in molten zinc, so you can prevent touch marks. After galvanizing, the baskets are loaded into a centrifuge, we'll see on the right-hand side here, for rapid acceleration and quick braking. It's not a speed of the spinning, but the rapid acceleration and quick braking that actually achieves the coating quality. And yeah, the things are being loaded out of into a quench bath for cooling and final processing. There's a sketch of a perforated basket for centrifuge galvanizing. It's a conical basket. The items reduces the possibility of rejects by curtailing overloading. So items are loaded up to about this point, so they experience the maximum spin and quick braking of the items. Oh, man. It also improves basket life. And yeah, you can see some threaded rod that's just come through the galvanizing process. We also have some semi or fully automatic plants now in existence in South Africa. So it's not all those archives that you see there. When the basket is sometimes overloaded, you sometimes have this type of thing. And nuts that haven't been prepared properly, and you get uncoated areas. So very important part, and this is extremely important for you guys as specifiers. The tiniest ordering of fasteners by the contractor for the project can eliminate a lot of this from happening. What we find often, the project starts, the items are fabricated and then galvanized, and at the last minute the bolts are ordered, and the guys are put in serious constraints by having to galvanize sophisticated fasteners for the project itself. The technique, oversized tapping of nuts to tolerance class 6AZ or centrifuge. This is basically what we use in South Africa. 6AX is cleaned by other methods, which is different to centrifuging. So there's no change to the bolt itself. This is what they use overseas, and it's a slightly different thing. The bolts themselves are marked with a U after galvanizing. So that's not used in South Africa. Nuts tapped oversized marked with a Z over here like this, or X, must never be mated with bolts and screws that are marked with a U, as in this process. Otherwise, it could result in thread stripping. Yeah, you can see an oversized nut. Hot dip galvanized nut. The 8 is a grade 8.8 and Z stands for the galvanizing, and this is the bolt that you shouldn't use with that. It's an 8.8 and it's undersized. So yeah, you can see the nuts are galvanized as blanks, and after galvanizing, they're tapped oversized to accommodate that extra coating thickness that you have on the bolt. And how that works is remember the cathodic protection that both Simon and Martin have talked about. There's no coating on the inside of the nut, but once you turn the nut up to its tension, there's ample zinc surrounding that area to give you cathodic protection. Standards, centrifuge hot dip galvanizing standard, SANS 121. This is the standard in terms of the diameters and the coating thickness that achieved with that, 50 or 25 microns. For items that are less than 6, we can't galvanize that, so it's about 50 microns. SANS 121 introduced in May 2000 and included all hot dip galvanized components, including fasteners. The ISO 10684 superseded this for fasteners in 2004. So from now on, when you specify hot dip galvanized fasteners, you must specify 10684. Here's a typical brief extract of the standard, different pictures of bolts, and obviously these are very much thicker and bigger bolts. Those are the typical coating thicknesses that one can expect to have. So this maximum coating thickness is only applicable to bolts and not nuts or washers. Here you can see 3 bolts subjected to a accelerated weathering test, zinc electroplated at about 10 microns, Sheridized at about 35 microns, and spin hot dip galvanized at 65 microns. And purely by coating thickness, the galvanized one has outperformed the others. Maximum of coating is only applicable to bolts, not nuts and washers. Here you can see some bolts. These are nuts that we measured 131 microns, and on washers 117. 131 microns will not interfere with the spanner action, so it's not a problem. So the method that galvanizing protects is a slowly corroding barrier, and you can see the 3 standards up here. ISO 9223 has distinctive classes of corrosion, C1 to C5 or CX, and we're just going to discuss this corrosion rate of zinc in microns per year in a C1 environment. Typical life of a zinc electroplated bolt, 10 microns, 50 years. I've capped these at 50 years. The mechanical plating and sheridized bolts are 30 microns, and the typical galvanized bolts are 80 microns. Just to be fair, if you look at C5, exterior industrial, and with high humidity and high salinity, it's about 4 to 8 microns of zinc loss per year. Not recommended with zinc electroplated bolts. Duplex coated recommended for these 2 bolts, and with hot dip galvanized bolts of about 80 microns, you'll get about 10 to 20 years of life. Yeah, you can see some, these are called buntons, which are basically the structural steel holding the vertical steel in a underground mine, which is up to 3.5 kilometers deep. And we realized that the fasteners that they had used, even though they were hot dip galvanized, the coating thickness didn't match the coating thickness on the bunton. So we duplexed all these fasteners and also fixed all the crevices so that there wouldn't be crevice corrosion prior to them being installed in a mine. Okay. Coating durability provides cathodic or sacrificial protection when the coating is damaged. Okay, you have, as Simon and Martin talked about, the electropositive materials like graphite, gold, and silver, electronegative materials. Down the bottom here, you see zinc and carbon steel. So zinc sacrifices itself to protect carbon steel. Sorry, ladies and gentlemen. Yeah, you see brass and zinc. Here's a typical example. This brass bolt fixed into a hot dip galvanized plate, and you can see it was fully immersed in water, and you can see the zinc is corroded away in preference to the brass bolt. Here's another one. You can see the water line. This is under in an immersed water condition. This is a galvanized plate, and these are stainless steel bolts, and they use the fiber washer, assuming that they would exclude this contact between the stainless steel and the galvanized plate. What they didn't realize is the bolts would not fit 100% in the center of the hole, except this one, which was in the center. All these actually contacted on the inside, and you had corrosion of the zinc coating in this instance. So electrolyte plays a huge role. You can see this is a wind turbine down in the Port Elizabeth area, and when I found it, it was put up in the 2010 Soccer World Cup. Strange enough, this was a coated, really good coating, came from Germany, I think, and this was all stainless steel. These stair treads and the side of the stairs. And what was seen is that the bolts were hot dip galvanized. So yeah, you had a small little anode and a big cathode, and I looked at it and I thought, okay, well, I'm really going to enjoy talking to the consulting engineers about their choice of material. And the first inspection was done in March 2011. And you can see the coating thickness 59 microns and then 84 microns on separate bolts. The last inspection took place in May 2018. That's about 7 years. And you can see, yes, the hot dip galvanized bolts, a little bit of discoloration, but the coating thickness is still well in 60 odd microns, and there's no corrosion prediction, no corrosion problems. And I think the biggest factor here is the lack of electrolyte, because it's 2 kilometers away from the sea. So in order to avoid cathodic protection or galvanic corrosion, can be prevented by selecting materials close together in the Galvanic series, reducing the electrolyte, controlling the anode-cathode ratio. The bigger the anode, the better it is, the smaller the cathode. For instance, the stainless steel roof, which is a big cathode with small anodes, would be a disaster, but the other way around with a zinc-coated roof and stainless steel screws will be a good idea. Effective insulation between the anode and cathode, as you saw in the previous example, and then add a third anodic metal to 2 dissimilar cathodic metals, using zinc where you have brass and steel together, possibly. Some novel configurations, yes, some hinge configurations, which you often see, instead of having this where the hinge is welded on site, starts happening like that after it's exposed, and ideally must be repaired. As you can see here, this repair looks terrible. Rather use something like this where the items are properly galvanized, properly fabricated, and there's no touch-up whatsoever. And here's another one, really sophisticated and good systems. Here's a third one. For security purposes, instead of using bolts and then welding the nuts and poorly repairing the coating, or otherwise using a punch and punching the thread for security purposes, there are these type of shear nuts, anti-vandal nuts, which are hot dip galvanized, and they finally, when you turn the nut like this, the nut turns off, and they are pretty secure afterwards, and there's no touching up necessary. Just remember that nylock nuts are not galvanized. If you use them, expect it that they be electroplated. Otherwise, use hot dip galvanized lock nuts. Here's another item to consider, using huck or lock bolts, which are hot dip galvanized if your choice is that. And obviously you have the huck bolt machine, and when you huck them like this, they are there for life. Threaded rod or holding down bolts, difficult to successfully galvanize. You can see these being galvanized, but they have to be cleaned off with wire brushes, etc., and not always the most successful. It don't have to be partially hot dip galvanized due to questionable bonding with the concrete. As Martin talked about, there's no change. In fact, there's better bonding if the whole thing was hot dip galvanized. You can see purposely hot dip galvanized foundation bolts are available, and alternatively a range of hot dip galvanized threaded rod in various diameters up to 3 meters are available ex stock. Finally, just talk about the difference between strain age embrittlement and hydrogen embrittlement. Strain age embrittlement, two things are needed. Stress induced in steel prior to hot dip galvanizing, cold working such as bending, rolling, punching, or shearing. This needs to be relieved prior to hot dip galvanizing. Strain age embrittlement also is caused by impurities in the steel, as Martin talked about. So note, should a crack appear almost immediately after hot dip galvanizing or handling, but not yet stressing, it is strain age embrittlement. And here's an example of it, and I'll show you various things of this and the reason why. You can see this crack in the steel after hot dip galvanizing. Here's another one. This one's a little bit out of the picture, but you can see this square tube here is perfectly hot dip galvanized without a problem, but this one has a problem. And you can see another view of it. It looks like a crocodile mouth. And what we did in the investigation, we found that when they produce square tubes, they take them and roll them from a round tube. And this particular tube had rolled more material into the corners because the natural dimensions of the square tube were less than the perimeter distance of the round tube. And that created huge stress in the corners, which obviously was relieved during the galvanizing process. So it's quite rare in galvanizing. I've only seen it in the 30 years that I've been involved in the industry twice. This is hydrogen embrittlement. Hot dip galvanizing. It rarely occurs in steel less than 1,000 MPa in strength, and that includes bolt grades 4.8, 6.8, and 8.8. Has a large grain size, so atomic hydrogen is released during the process. Hot dip galvanizing, only one source of hydrogen, and that's in our cleaning liquid. Zinc electroplating has two sources of hydrogen. More chance of it occurring in steel are greater than 1,000 MPa, which includes the bolt grade 10.9. It has a small grain size, and therefore atomic hydrogen is not released. So one has to control for that. And you can see hydrogen is one of the smallest atoms you can actually get into anything in the steel, pores in the steel. Only observed after the bolt or nut is stressed or loaded. And here you can see basically what happened with this particular one. I think this was overseas somewhere. Can be avoided. Designer to select a steel of less than 1,000 MPa by making use of larger or more grade 8.8 rather than less grade 10.9 bolts. Manufacturer responsible for suitable manufacturing techniques. Deliver high strength components such as 10.9 bolts to a reputable spin galvanizer timelessly. Very important. Hot dip galvanizer according to that standard. Galvanized and mechanically clean. Wheel abrade grade 10.9 volts. As you can see, this wheel abrasion machine here. Then the galvanized to flash pickle components in inhibited hydrochloric acid for about 30 seconds. Galvanized not to overload the baskets to generate maximum spin and quick breaking. You can see again the maximum 4 points, so we can actually get a rapid spin of the items rather than they not spin at all. And if hot dip galvanizing is unsuccessful or too thick because of overloading the thing, dispose of the bolts and do not strip or regalvanize, because that can create major hydrogen embrittlement problems. Alternatively, import from reputable overseas suppliers. Very important again to make sure that short fasteners are ordered shortly after the project is awarded. Thanks very much. Thanks for enduring me.
Thanks very much, Terry. It certainly looks as if design engineers will need to make sure that bolts and nuts are hot dip galvanized for their projects. Right, we're going to move now to the Q&A. We've received some questions in our chat function, so I'm just going to quickly scroll through those. Give me a few seconds while I look for that. There was one question that was directed to Martin, and that question is, it's coming. Let me just keep looking. To Martin, is it possible to decrease the concrete cover when using hot dip galvanized rebar?
Well, it is possible, but I would say it's not recommended. I would continue to follow the same design principles for black steel, but you will have a much longer structure life because you're using the galvanized reinforcing steel. Because the superior bond strength, we've also been asked about, using not less rebar, but less overlap lengths. Is there a way to optimize or minimize the use of steel? I think this is a major research project. We have not undertaken this, but I think the recommendations is follow the same design guidelines as for black steel when using hot dip galvanized rebar.
Thanks, Martin. Simon or Terry, is there anything else you'd like to add?
The only comment I would have is that this week there was a project where there's a building that's been, or a structure that's been set up. I think it's called the Cube in Germany, where instead of using steel reinforcing, they're using a carbon mesh as a reinforcing. And the idea is that when you manufacture cement, the actual manufacturing process in the kiln produces so much carbon dioxide that it contributes, the total cement industry contribution to global warming is apparently quite huge. I have a figure of 19% of CO2 emissions worldwide, but I stand corrected. However, it is significant. So in order to reduce the creation or production of cement, the test work's being done to use carbon mesh in reinforcing concrete. And with that process, you can then use thinner sections, and the net result will be a reduction in the use of cement, which would then reduce the CO2 emissions, if I understand the press release from a Berlin research organization during the week. There was a concrete and cement conference held at the University of Cape Town under the Department of Civil Engineering, where there's a concrete rebar specialist, Professor Hans Boyshausen, and frequently the question would come up, can we reduce the cover? But in reality, the answer was always what Martin said, keep your cover. Particularly in Cape Town, I can tell you that along the Mully Point, Greenpoint coastline, in the same location, in fact, within 200 meters of the sea wall that Martin showed you when he was speaking, there are numerous residential apartments where massive concrete repair jobs are being carried out at this moment to repair corroded rebar as a result of the low cover over the concrete, or the fact that the coating over the concrete wasn't adequate, and the expense to the body corporate or the residents was enormous. If you go along, if anybody's in Cape Town and wants to take a look along the Sea Point, Greenpoint, Mully Point coastline, you'll see many of the buildings there. Some even have been repaired. They've been rebar repairs, and you could already see the red oxide coming through cracks in the concrete and through the paint. So, as Martin said, stay with your cover and galvanize your rebar.
Terry, would you like to make any comments?
Yeah, I just want to say, Martin, you had a very interesting building which had those scallops on, which you said was for heat transmission in the building, even though it was about 40 years old. And you mentioned that the cover was about 1 inch, which is 25 millimeters. And reflects, in my talking to the Galvanic Association in Australia, they have also gone the route of looking at minimizing the cover in certain strategic places to the advantage of the design engineers for lighter structure by using galvanized rebar. And just one last thing, we have a Groote Hospital down here where, when I was involved many years ago, and we're looking at about 30 years ago, where they had precast panels where they had to use that, and they used the mesh was galvanized, and there's no spalling whatsoever. Although it's not a marine atmosphere, it's probably a C3 atmosphere, or maybe a C4, and there's no spalling whatsoever. So I think there is merit in looking, and I understand the 4Cs, make sure that the concrete cover, compaction, curing, and all that is correct. But there is merit in looking at that, because it's a huge advantage to the design engineers, and particularly the architects that come out with these little thin structures. And if you can overcome that issue internationally with the Zinc Association, that will be a great benefit to all of us, I think.
Oh, well, good point to talk about the precast structures, because certainly there's a lot more control of the alignment of the rebar and the thickness of the cover. Field installations, sometimes it's a lot more difficult, and even I've seen rebar, either it's protruding, you know, they remove the formwork and then there's a rebar right at the surface. I think in the precast industry, you're right, some of the examples I showed had very thin cover, 25 millimeters, but much easier to control in that environment than in a field installation.
Martin, can I ask you, have you ever seen rebar and what is your comment on it in terms of galvanizing and non-galvanizing in so-called foamed cement or foamed concrete? I had a client that came to me some years ago, and they were looking at building low-cost housing and various other structures using foamed cement, foamed concrete. There's quite a lot of work done at the University of Stellenbosch in Cape Town, near Cape Town, on foamed concrete, but I'm not sure how much of it is actually used in industry. Do you have any experience with that?
No, this is the first I hear of foamed concrete, so I can't comment on that. But we have seen developments here in North America are fiber reinforced concretes, as you were talking about carbon fibers, but also steel wire, galvanized steel wire, and polymer fibers to try and densify the concrete and reduce cracking. We've done some work, the Federal Highway Administration at the University of Kansas and also at the Texas A&M University. So the width and severity of cracking is greatly reduced by using galvanized rebar compared to black rebar or epoxy coated rebar. And we relate that to the superior bond strength. It keeps the concrete in place and doesn't allow the cracks to form with or without fiber reinforcement. But I'm not aware of the foaming concrete. So this is just quite aerated, so it must be very lightweight.
Lightweight structures so they could create panels and systems quickly.
Mm-hmm.
All right, I'm going to move on to the next question that we've got. I think this one is aimed at Terry. It's a question from Dennis White, and he asks, is there an increased risk of crevice corrosion with oversized tapping of nuts?
I've never seen that before, ever. Dennis, nice to hear you listening to our seminar. I'm not quite sure in what form you're talking. I mean, a crevice corrosion happens because there's a small air gap in certain conditions. I've never seen it on bolts or nuts. Maybe you can expand on your next question or send us an email and we'll answer it.
Terry, I could perhaps comment on that. Essentially, what you've got in the system that you're creating with the galvanized bolt and then the washer is that you've actually got the whole gap closed up. And when the galvanizing actually oxidizes in the atmosphere immediately, once you put on the nut, you've actually got quite a hard oxide layer already in there, and the chemistry of that material will then prevent moisture or liquid actually creeping in there. The essence of crevice corrosion is that you've got two environments, the outside environment where you've got oxygen and the inside environment where you haven't. and you get what we've seen, as you and I have seen on many occasions, the differential effect, as well as in the crevice itself, acidity picks up. But because the nut and the bolt are so tight, it's impossible to, it's actually impossible to, well, not impossible, but it's very difficult for moisture to actually get into that tight fit between the bolt and the nut. Those would be my comments.
I can say something further. What I didn't mention during the course of the seminar was that in grade 8.8 and high strength steel bolts, it's obviously recommended, and a lot of manufacturers do a material or a factory lubricant on the fasteners so that when you tension the bolts and nuts, it doesn't gall up at a certain tension area. So that lubrication would also play a huge role in preventing any crevice corrosion that may form between the two surfaces.
Great, thank you very much. The next question we've got is Brent O'Callaghan asks that some standards do not permit hot dip galvanizing in underwater use. A French water association recommended hot dip galvanizing steel work in water treatment or desalination facilities where the steel is permanently immersed. Any idea why most standards do not recommend immersion, ionic disbondment issues? Who would like to take that one?
I think what Brett might be referring, sorry, Martin, go ahead.
Well, I would make a comment. It's not a coating disbondment issue, but depending on the underwater condition, I mean, zinc can be quite rapidly attacked in seawater, and so the life of the coating will not be quite long. If the water is more stagnant, we can have a longer life. If there's lots of wave action, that will accelerate the corrosion. But it's just a straight consumption of the zinc that is accelerated in seawater. There are alternatives. There is a zinc 22% aluminum alloy that is used for thermal spraying, and this has quite good corrosion resistance in immersed seawater conditions compared to a pure zinc coating. But this is another coating technology and not available through hot dip galvanizing.
Simon, would you like to make any comments?
I'm not sure what he meant by ionic disbondment. I've got a feeling he means cathodic disbondment. And I suspect that he's got a structure that's been given some sort of active cathodic protection system. In other words, there's what's known as an impressed current cathodic protection system that's been wired up on the structure. The structure's immersed, it's galvanized, and then I presume that's what he meant. If it's not, maybe you can just type up a question to us and or come on. I mean, I'm sure he's on board. Maybe you could ask the question and he could free it up and tell us quite what he's referring to. The other comment I'd make is that if you're using, remember I mentioned in the chemistry section that zinc is amphoteric. So it will be attacked in an alkaline solution as well as in an acid solution. If you're in a wastewater treatment works or even a desalination plant, you've got weird water chemistry there. I mean, if you just take wastewater, the combination of materials in wastewater is absolutely amazing. You've got industrial effluent, which flows into wastewater plants. And then you've got domestic effluent, which includes basins, showers, baths, lavatories, toilets, and everything else that people pour down drains. And when you manage a wastewater treatment works, you actually have to take into consideration that sort of chemistry. I would imagine that hot dip galvanizing on its own would take massive strain underwater in effluents or liquors, we call them liquors, in the wastewater treatment works. And if you're going to put it in, then I would say that a powerful duplex system would be better to use. So you would, for instance, in South Africa, there's a company called Corrocoat, and they provide very tough, resilient coatings for very unusual systems. They're hard, they're very, very resilient. So if you apply that over hot dip galvanizing, then you would have what I'd term a fairly bulletproof coating. So when the organic coating collapses, then the zinc coating goes next. But remembering that the zinc will react, if it's as it's amphoteric, it will react. If it's acid or if it's basic, you'll get a rapid reaction. And then Martin also mentioned wave action. So in wastewater treatment works, there's a tremendous amount of agitation. In the initial tanks, they've normally got aeration blades where they aerate the ponds at an enormous speed in order to aerate and react with the bacteria in the system in order to digest. They would call them aerobic digesters. So you want to digest the liquor to start breaking down all the various organic compounds in the system. And then you have a variety of other reactors, all of which are agitated. That alone will start removing zinc oxide, zinc hydroxides. So I'm not sure what that French standard is, but I wouldn't go that route. I wouldn't expose naked, I mean, Terry, I don't know what you think, but I wouldn't expose naked zinc galvanizing to the liquor in a wastewater treatment works.
In standard water conveyance situations, hard water, which has got scale forming properties, will work very well with hot dip galvanizing. I remember a colleague of mine up in Johannesburg, where the water is quite hard, getting 40 years of life out of his galvanized pipes. Whereas if you come down to the coast, the water is a lot more softer, do not have too much calcium carbonate in the water. And then galvanizing is not the right choice for that. And then obviously there's other materials and coatings to work well.
But that's only fresh, that's potable water you're referring to, eh?
Yep.
That's potable water system, yeah.
No, but fresh water versus salt water, that's a big part of the discussion too for immersion applications. There is a comment here that the paint coatings over hot dip galv underwater do not work reliably, and certainly there can be a lot of variation, but almost all of the failures of duplex coatings that I have seen, premature failings, it's the paint has not been applied to specification. So that might be a factor that's causing the uneven performance that's being observed. But definitely straight zinc coatings underwater have a certain life, but much reduced compared to atmospheric exposure.
Yeah, what Martin talked about, this one thing, last one for me, is the splash zone of the sea is the most aggressive area in most situations, and even heavy materials will take flak in that. But deep under the seawater, in the seawater itself, galvanizing a good thick galvanizing could probably last about 10 to 15 years, provided it is completely immersed in the water.
Thanks very much. Brent, I have allowed you to speak. So I'm going to ask you to unmute if you would like to ask your question to the panelists yourself. See if you'd like to, otherwise I'll just go ahead. There we go.
Thank you. I think I'm heard.
Yes.
Thanks very much.
You can go ahead.
We can hear you loud and clear.
Just want to say thank you very much, Simon. And the questions have been answered in the chat. I'm not sure if they went through on the Q&A section, but I commented that the paint coatings over hot tip galvanizing underwater do not work reliably, meaning that was where the issue of cathodic despondent, or as some people call it, ionic despondent, I've seen it referred to as both, that seems to have been the problem. I was just wondering, going on from that, if you could possibly make any comments on, for the purpose of engineers wanting to specify correctly on our drawings or on any consulting engineering practices drawings, how to overtap nuts, which standards should we be referring to? How do we work with ISO 12944 Part 9, which specifically specifies CX coatings for extreme conditions offshore, and IM4, which is immersion coatings in seawater under the presence of cathodic protection? Those are really our interests, which, you know, these are very important things which appear on drawing after drawing. So one wants to make sure that one gets it right. Thanks.
Brent, you just want to, sorry, there's quite a lot to absorb there. Can you just fire off your first question and that's the one about part 9 of ISO 12944, is it?
Well, ISO 12944 Part 5 previously specified for carbon steel substrates various coating systems, and you had an IM2 corrosivity category for immersion under seawater, as opposed to IM1, which was in fresh water, and then IM3, I think, is, I forget exactly, IM3 is for buried service underground, where, of course, you could have some presence of water. But they've now upgraded ISO 12944 Part 5 and brought out a new part called 12944 Part 9, which deals specifically with category CX, which is offshore, typically offshore marine splash zone on things like the mast gas jacket, for example, the areas of the pile's legs or the jacket legs which cannot be serviced, and also the parts that are permanently immersed, which it's now called corrosivity category IM4, which is its immersion in seawater under the presence of cathodic protection. And that is where the whole question of cathodic disbondment comes in. Previously, ISO 20340 covered a whole range of tests that had to be applied against the disbondment. That has apparently been now built into 12944 Part 9. So straight away, we're moving from C5 marine into CX and IM4, which is a little bit different from what the industry has been using for the last, say, 20 years. That's what I was saying.
Well, the CX only, all that CX does is it just shows normally they use the rate of the rate of corrosion, or the rate at which corrosion takes place in microns per annum for a selection of metals. So it would be zinc and iron. And what they're doing is essentially it's CX. They're just showing, I haven't got the table up in front of me, but Terry, you had it on your computer earlier on. They're just showing a higher rate of corrosion, as far as I'm aware, on the table for CX. But if you're and that would be atmospheric, that's not immersion. CX is not immersion. CX is just exposure in the atmosphere in an environment where iron and zinc, I think there might be a third metal, copper possibly, but let's just say iron and zinc for the discussion, the rate goes higher. So at C5, what used to be C5M, you might say of, I don't know, 8 microns per annum of zinc and 10 microns of iron. If you go to CX, it just goes higher. But the whole of ISO 9223 and those classifications is based on sulfur dioxide, chlorides, time of wetness, and relative humidity and temperature. If you're going immersed, then there's a whole different ballgame. And obviously, if you're in an atmospheric environment, you won't be applying impressed current cathodic protection because you've got no electrolyte. If you've got an immersed structure, you will be applying you may be applying impressed current cathodic protection, or you might be applying passive cathodic protection with passive anodes. I can't remember now. I don't know if Martin, if you can know it, or Terry, but I can't remember the criteria for cathodic disbondment. I think you have to control the power supply of your cathodic protection system very, very carefully in order to prevent cathodic disbondment. But some paint or coating suppliers actually note that their product is not vulnerable to cathodic disbondment. And that in my mind would be the chemistry of the coating. But Terry, maybe you and Martin, you would be able to comment further.
I'd just like to say, maybe Brent, this is quite a heavy topic for us, and we'd like to mull over it, I'm sure. Is there a possibility that you can put it on an email and send it to one of us, and we can certainly come back with some accurate answers for you in helping you to discover which is the way to go?
Yes, thank you very much, Terry. We've been, over the years, looking at the recommendations of the South African Hot Dip Galvanizing Association and jumping around from one ISO standard to another. And when everything changes like this, it's good to get some expert advice. So thank you very much.
Brent, one other thing I could say is it always helps us if you actually give us a specific case where you had something that worked, and then suddenly you had to change to another standard and it didn't work. Regrettably, there might have been a failure, but that often assists us to be able to discern exactly what's going on. Otherwise, I agree with Terry, we'd have to dig into this and go and look at 12.944 Part 9 and all the various other things, and then come back to you on it.
Well, I think in answer to that, Simon, thank you for the time allocated. Not talking about previous failures, we have experienced a previous underwater failure of an epoxy coating over a zinc galvanized surface. In actual fact, the corrosion specialist at the paint company said that it should not have been hot dip galvanized and allowed to be in a tidal zone. So things like that are of interest. But the question that we're really raising here is whether CX and IM4 are in fact the same thing, because they're specified as the same coating in the table in the latest 12.944 Part 9. Without going into detail and boring everybody, we're just looking for a sort of a clear roadmap to go forward and say that this is a CX structure because it's an offshore jacket, or it's a piled jetty structure. And once you've painted it and put it into the sea, you can't go there and paint it every couple of years. And it's not underwater because it's tidal, and it's maybe splash zone with maybe 5 meters of wave height coming through at different times, like you have on the Moscas platform. You know, it's something that you can't access to maintain. So it's interesting to know what is CX and what is IM4, and how do we move forward under the newly specified standards as opposed to the old systems. That was really the nature of the question. Thanks again.
Okay.
Right. Well, thank you very much, Brent. As Simon mentioned, they will get back to you after the seminar. I think we've got time for one more question. So this one is from Dirk Kruger, and he asks, can spring washers be hot dip galvanized, or is it better to use lock nuts instead of spring washers? Terry, would that one be for you?
Yeah, I've come through an industry, and obviously Martin stands in a different, more sophisticated country than South Africa. But we've introduced hot dip galvanizing on 12.9s in this country from a number of years ago, and because of archaic methods here, we had a lot of egg on our face. So we went away from 12.9s. That's why I said you have to strictly follow a standard, get a reputable galvanizer to do it, and ultimately you might have success, or otherwise import the 12.9s from overseas. Much the same as spring washers. You're dealing with high strength steel, and if they're not dealt with correctly, I would say the more safer route to go is to possibly mechanically plate them, or alternatively use your lock nut as you suggested. And mechanical plating for that particular application would be pretty safe, and I'm sure that would give you a very good performance in terms of corrosion protection.
Great, thank you very much. Is there anybody else, Martin or Simon, who would like to make any comments before we end off?
No, nothing else from my side.
Great.
Anybody else got any verbal questions? Anybody else? There, I see there's a chat somebody's put. Oh no, I see that's. Have we covered everything, Shannon?
It does look like it, yes. And the Q&A, there was one question that you did answer that was also from Brent. So I think we've covered all of those. And then I think that does bring us to the end of our session. We have run out of time, unfortunately, as well, but we do thank everyone who participated in our live Q&A. If you didn't get a chance to ask your question, or if we didn't get a chance to answer you, then we will happily connect with you after the webinar. And this now brings us to the end of our session. I'd like to take this opportunity to say thank you to our panelists, Terry Smith on hot dip galvanizing, and Martin Gagne and Simon Norton from the IZA Global team on galvanized rebar. A special thanks also to Kevin Watson from the South African Institute of Marine Engineers and Naval Architects for arranging the CPD points. I want to thank all of the attendees for taking the time to join us to talk about galvanizing of rebar and bolts. If you'd like more information, please be sure to visit the International Zinc Association's website at www.africa.zinc.org, or you can contact Simon Norton on 082 831 2924 or email him at zinc@iafrica.com. The recording of today's webinar will be sent to you in due course, and if you have any additional questions, please do be in touch. You can reach us at shannon@creamermedia.co.za. I'll hand over now to the panelists if there's anything that they would like to say.
Just make sure you galvanize everything.
There you go. Terry?
Yeah, I just want to apologize for my computer, and I think I know why I did that, but thanks for indulging me and giving me an extra little bit of time. Nice to see you, Martin.
Yeah, very nice
Yes,
to meet you, Martin. Sorry to wake you up so early in the morning in Mexico, where you're broadcasting to us here in South Africa. And also thank you to Kevin Watson from the South African Institute of Marine and Naval Architects, who facilitated the CPD points for engineers. And to all those engineers, ladies and gentlemen, thank you very much for participating. And we have part of this process or this webinar, there are zinc matter publications, and they deal with hydrogen embrittlement of bolts and strain age embrittlement as well. So you'll get a very good background in that once you get that sent by Creamer Media. And please contact us if you need any further advice on galvanizing, zinc coatings. Anybody comes to you with cold galvanizing or all these other names, we can assist you. Thank you very much. Thank you, Terry, very much for your expert detailed presentation on bolts. It was superb.
Yes, and thank you as well for the opportunity. And I did enjoy your presentation, Terry. Very well done.
Thanks, guys. Thank you, Shannon.
No problem.
And,
thank you very
Renette.
much, everyone. I really appreciate it. And thank you to everyone for attending. Keep well, stay safe, keep warm, and we'll see you in the next one. Thanks so much. Goodbye.
Okay.